So hopefully we'll get through most of the transform and class and the related type dispatch class today, but let's start with the context, because without it, it kind of becomes, it's fairly complex as it is. So it's important to have the context and to kind of understand where we are in the code at all times, at least. Otherwise, I feel I'm lost and you lose the forest for the trees or vice versa. So again, just to set ourselves, we're trying to understand what is required in the transform class in order for us to be able to support all the functionality that we saw earlier. If you recall, I think it was 2 sessions ago, we looked at the various functionality, how transform could be created using decorators, supplying the encode decode function. So essentially a transform class needs to be able to support all that functionality. So if you subclass from it, and if you add an encode or a decode or a setup independently, it's able to support those, able to dispatch a function based on the type of the data you provide it, and so on and so forth. So in order to do that, you need to create a special type of class, and that's the reason meaning Jeremy, uses a meta class. But in order to understand a meta class, let's start with the simple class and go from there. So we've seen this before, so I'll move a little bit quickly through it. But essentially, when you say class foo and then pass in Python, it creates a class for you. And that's essentially syntax sugar for a type constructor, and a type constructor is basically a class constructor, and that a type constructor requires 3 things to be provided to it. One is the name of the class, the second is the set of classes that it inherits from, and therefore the base classes. But since we just want to define the class foo2, we just inherit from object, because eventually object is like the source of all Python classes. Source, but all Python classes eventually inherit from object, and then a dict that forms the namespace of the class, as we'll see shortly. So you provide foo2, or you provide the name, the base classes, and an empty dict to foo2 type constructor. That's the same as constructing the class using class foo2. And so if you compare foo and foo2, you find out that they're identical. If you check the type of foo, then it says that it's of type, and the type of type is also type. So essentially what that means is, in Python, type is a class, and type is also a constructor of a class. And so if you look at foo2 dot, and then you'll see a bunch of attributes of the class. And one of the important attributes is its dunder dict. And the dunder dict, in fact, it turns out, is the dict that you provide to the type constructor. And there are some reasons why a weak reference is, it's a special type of dict with some ability to garbage collect, and when its last reference is gone, blah, blah, blah. Details aren't important right now, but the point is that we could set an attribute in the dunder dict, and such as A is 1. And what that means is the A attribute within the dunder dict of the foo2 class is set to 1. And that is identical to the normal or syntax sugar way that we typically do it, which is to say declare an attribute A equals 1 within the class. So those two things are exactly equivalent. So when we do class foo2 A equals 1, it sets the attribute A to be 1 within the foo2 class. Now, how you access the foo2.a attribute within the class is also the easy way to do it is obviously do it foo2.a. But what you're actually doing, and Python internally translates that to foo2.dunderDict. And that's how you get access to the attribute. So why is all this relevant? This is relevant because, again, as I said in the beginning, we are proceeding towards creating a meta class which will help create the transform class, which we need. We need the transform class to be special to do all of the functionality we desire from it, and therefore a normal type constructor won't work for us. We need a different type of type constructor or class constructor, and that's why we're trying to understand how a class is constructed so that we can modify it. So Jemmy can modify it. So typically, in order for you to create and use a meta class, what you do is the syntax that's followed is to say class, my class. That means the class you want to create using a meta class. If it's different from type, then you provide meta class equals whatever the name of the meta class is. If you don't say anything here, it just uses the type meta class to construct the my class. So that's what this says. And let's therefore create kind of underscore M meta class as a toy example in order to understand better what a meta class does and head towards this underscore transform meta, which is the class we want to create that creates the transform class. So remember again that type requires three things: the name, the basis, and the dict. And therefore, in this class, meta class underscore M, we could create it from scratch, but just like with everything else in Python, it's easier to inherit from the type constructor and then modify what we want to modify. So we create underscore M class, inherit from type, and then modify its dunder new method. And the dunder new method is what gets the name, basis, and dict. And here, as you can see, we don't do anything. We just say, oh, give me back the superclasses new with, and whatever name, basis, dict I pass to you, pass it to the superclass, which basically means that underscore M, even though it's a meta class, doesn't do anything and just passes it to type. It's reusing the type. So it doesn't, in effect, do anything other than illustrate an example of a meta class where we modify, or where we can if we wish, modify it under new. So that's what this says. And so if we now create a class T, and as I said before, the way to create a class using a different meta class than type is to say meta class, what the meta class name is. So we pass that underscore M, and since we aren't doing anything, we just define it. And you'll see that T is no different from foo or foo2. That's also a class just like foo or foo2 we defined earlier. So then if you look at dunderDict, it again has the same things as what foo had. Now let's see whether when we change something in the meta class, then what begins to happen. So here it's a very simple change. We just introduce a print statement before returning the new from the superclass. So that's the only change we made. We've just added a print statement. But, and then again, we define class T. But what is interesting or fascinating here is, even though we've just defined the class T, we have not even instantiated it yet, it prints the statement that's included in dunder new. So what this tells us is the fact that dunder new is for the class T, the dunder new of its meta class is run when the class is defined, not when the class is instantiated. Like when I say instantiated, I mean you could do, let's say, small t equals t brackets, which instantiates or creates an instance of the class T as you would normally instantiate any other class. But in this instance, we don't even need to instantiate in order to see this print statement. So again, to repeat, what it means is the new is run when the class is instantiated. So that's the key thing we take away from this little experiment. So if we look at the meta class for the transform, which is this TFM meta. So it's a meta class for the transform class, and it's custom defined. So we just use it internally, hence the underscore in front. So the things that Jeremy has done in the meta class which defines the transform class is inherit from type, and has changed the new definition, the call definition, and the prepare definition. So those three things have been changed. So going back to where we were, you see that if we look at, we've looked at the transform meta class below, and we're replacing three things, and we'll kind of understand how and why those modifications are necessary and how they help us create the transform class. In order to kind of dive into the details, and Jeremy goes through it in his walkthrough video, the point being that you really, in order to understand all that is happening, you would kind of go through and read. He says he spent many weeks, if not months, going through the details of Python's various capabilities, and specifically he points to the class creation details, which is there in this particular data model, which has a lot more detail. But this customizing class is what he's referring to. So they begin to talk about meta classes, how you specify a meta class for a class. The first thing is required in meta classes is to resolve what is called the method resolution order. This is necessary and becomes much more important in multiple inheritance, not so key for what we're talking about here. But the next critical thing is preparing the class namespace, which is where the prepare attribute comes in, and it's a class method. So, and you need to kind of pass into the namespace. So you say meta classes prepare, and you pass in the name basis and the keywords, which is a ** keyword, which is essentially the dict that you pass to it. And then as it happens, that namespace prepared by prepare is then passed into the new of the meta class. So that, and then from there, he dives into the customizing the class creation. You can click through the links, and then you can chase it down to what it means for type, and then you can go through the rabbit hole in more and more detail. But for our purposes, this ought to be enough to indicate what we need to do or focus on first is to create or passing the right parameters to the prepare method of the meta class. So if we look at the meta classes, so we need to prepare the namespace, which is the dit object that's passed in. And for details of the namespace, I provide a bunch of references that you can look at. There's also a whole bunch of references and videos for meta classes that you can watch and learn from. But let's now focus on what we want to do with respect to the toy example we are using to illustrate what we want to do with _transform TFM meta, which is the actual class or meta class that we want to develop. But sticking with the toy example, what we're doing now is just adding a class method. Remember the documents up above said you needed prepare to be a class method, and it needs to return a dict. So that's what we do. We define new. This is the same new as we had before. And then we pass it a class method. So now if we define again the class T using the newly defined class M, if you recall, it'll print, we have added the print statement, and then everything else looks the same as before. Now, if we start sticking in some things to the dict we return from the dunder prepare of the meta class, such as a equals, or a dict with a value of 1, then and then define the class T using the meta class underscore M, then you'll begin to see that the dunder dict in the class T now has the attribute 1. So this is a way that you can insert attributes into every class that's created using the meta class M. So every class that's created using the meta class will now have an attribute, class attribute A1. Now, so that kind of tells us what is going on in the TFM meta class below, right? So what we see, however, in the, let's go to the TFM meta class. So in the underscore TFM meta class, we've used, just like the toy example, dict that's returned when we use prepare. But what we observe is it's not just a standard dict, it's a TFM dict. So it's still so now we begin to look at, oh, what's a TFM dict as opposed to a standard dict? So we go up here and we see the definition for a transform dict. So what is a transform dict? A transform dict, thankfully, is something we inherit from dict. So it is a dictionary. But how is it different from a standard dict? Well, a standard dictionary, as some of you may be aware, the details of Python, it has set item, get item, dunder set item, dunder get item defined within it and stuff. So this particular transform dict inherits from dict and overwrites the set item. And how does it override the set item? So what it does is, if the key for the set item is not in the list of methods given in TFM methods, so if the key is not encodes, decodes, or setup, and the value we passed to the key is not a function, because anything callable in Python is anything that has a dunder call, which in essence, you can abstract it as classes or functions in general. Actually, more specifically, anything that has a dunder call is a callable in Python. So what it says is, if the key is not encodes, decodes, or setup, or the function or the value that you pass to the key is not a function or a class, then don't do anything and just use the dunder set item of the dict. That means it just treats it as an ordinary dict and just updates the value for the key that's provided, if the key is not one of these special types, I shouldn't say types, special string values. If, on the other hand, the key we provide to a transform dict is encodes, decodes, or setups, then see what it does. If that key is not already in the dict, then for that key, make the value a type dispatch object. Right now, we don't know what that is, but it's just making the value for that key, if the key is encodes, decodes, or setup, a type dispatch object. And if it is not in the dictionary already, if it is in the dictionary, then it says execute the add method of the type dispatch object, because there isn't an add in a dict. This add is actually a method of the type dispatch object, which is actually a class. So, so it then says add the value to the key for within the type dispatch object, or run the add method of this type dispatch object and set the value for this key to be V. So again, to repeat just again to set the context, what we are doing here is preparing the namespace of the transform meta, of the transform class in the transform meta class. So what we are doing is in fact defining this dict. That dict, which is in a normal class, just a regular dict, is of special type, transform dict, which does nothing and just returns a regular dict if the key is not one of these three strings. If it is one of these three strings, and if it's already not in the dictionary, in the TFM dict, if the key is not already in this dictionary, then it creates a type dispatch object corresponding to that key and adds the value V, which, because we have checked for it, it will be a function. It adds a function corresponding to that key, sticks into the transform dict. And then that dict is what is returned, okay, as part of our preparation of the transform class's namespace. So that's kind of what is happening with the transform dict class, or is the purpose of the transform dict class. Now, as we saw just in the transform dict, a type dispatch object is what is created as the value for the key if the key is of one of these strings, encodes, decodes, or setups, right? So what then is the type dispatch object? In other words, what we can look at also as example of the transform dict is if we run a class A, sorry, I forgot to run these code before I use the example. So if I define a class A and I say my meta class is underscore transform meta, and I define an encode and it's simply returning the value X, you can see that it A dot encodes says object, and then pointing to an arrow and says encode. So this is not a normal function that you typically see. And a type of, if you check what type A dot encodes is, it says it's a type called type dispatch. That is essentially what's happened by using this particular line, which is it sets the value to be of type dispatch, or it creates a type dispatch object, which then means we need to understand better before we understand all the details of the transform class. We need to understand what is a type dispatch object. So that type dispatch object is defined in a notebook by itself. So instead of this notebook, we are off, and let me know if you can still see my screen. We are off to the O3 dispatch IPNB or Jupyter notebook by name O3 dispatch. And again, it's also in fast core. Can people see the screen and the type dispatch notebook that I have?
Yes.
Yes, no?
Yeah, yes.
Okay, thanks. So now I'm just going to go through some of the helper functions. Remember where we are. We have defined the namespace and returned a TFM dict as part of the meta class which defines a transform. And the TFM dict, if the string is a set, encodes, decodes, or setup, creates a type dispatch object. And we want to understand what a type dispatch object is. Now, letting the cat out of the bag a little bit, the type dispatch object obviously is going to be the thing which enables us to check on the type of something that we give as input and then dispatch the function corresponding to the type. But we then within the notebook see the code that enables us to do that. So some helper functions which help us understand how this works. So there is apparently a type hints functions within Python itself, but then Jeremy, as his want and also for legitimate reasons, modifies the type hints that's the default in Python and adds the else empty dict thing. And in the interest of time, I'm not kind of going to check through type hints, but that's how he's modifying the type hints. So this typing dot get type hints essentially in the newer Python, I forget which version onwards, it began to support the type hint capabilities where you can provide hints of the types for your various things that you pass in and for the return. And it helps you collect or get access to those. And he modifies that in order to return an empty dict in certain conditions. You can look at the code for typing.get type-ins yourself. But here is an interesting function that he uses, which is annoret. And this is short form for return the annotations of func. And we'll see, instead of going through this code, we'll kind of observe what the code does, as that's a lot easier to understand. Just going to run this code. Now let's look at how this annoret helps us get the return annotation of func. What that means is we'll be focusing on the type. We'll be trying to get the type of annotation, or we'll be trying to get the type annotation on the return, not of the input, mind you. This annoret is focused on getting access to the type annotation of the return, not of the input. We'll do the input a little bit later. So here, if you define f, the input type is int, the return type is float. So if your annoret is working correctly, which is this code here, then the annoret of f should give you back float. Therefore, you check for equality of annoret of f being float. Here, he just removes the input annotation, and that should have no effect. So you should still get float. Here, the return annotation is a more complex type. It's of typing.tuple float float. And what you get should be typing.tuple float float. It's just whatever type you return, whatever type you define for the return is what you get here. Now, in this case, I think these are notes I made for myself, but he tries, I believe, to differentiate between defining no or a none annotation on return, in which case this code up here on annoret gives you back a none type, as opposed to no annotation at all on the return type instead of a none, and that gives you a none back. And it's my guess that the reason he does that is, in one instance, as I've said in the comments, you want the type dispatch to return to you whatever Python is returning as part of the return function. In the other case, you return whatever input type went into you as the output. And you won't be able to distinguish between those two if you didn't have this capability. But whether or not he uses it for that purpose, the point is that if you define a none, then annotate returns a none type, as you can see from this equality checking that he does. And then when you actually don't define anything, then it returns just a none. So that's what all those checks are for. Then what he does is he uses functools, and functools in Python, if you haven't spent time on it, is something fun to spend time on because you will learn a lot about some cool capabilities that are buried in that module. One of the things is a compare to key essentially says that whatever key you pass into this is something that's used to classify or it's used to sort the values that you pass in. So in this case, what it does is if A is a subclass of B, then it does all this. If A is not a subclass of B, what you get back from this is a -1. If A is a subclass of B, then it sorts it into two different categories depending on whether A is equal to B, then it returns 0. If A is a subset of B, then a subclass of B, then it returns a 1. But the key thing to take away from it without getting buried in the details is it's a key to sort A and B based on subclass classification. So here's an example which makes it clearer using a TD class. And by the way, there is a numbers hierarchy in Python, which is there. There is the numeric tower. So if you can see, it defines all of, so the numbers.number is kind of sitting at, it depends on the root of the hierarchy, and then there are various subclasses that get defined below or above it. And the point is that numbers.number, as I said, is the root. Then there is numbers.integral is a subclass of that, and int is a subclass of even that. So given given a dictionary TD, which has these three classes, which are subclasses of each other, then the sorted function, which uses the CMP instant to sort it, sorts it in this order. So what you see here, and this will become important as we dive into the details, and there'll be a particular reverse call, which kind of, you'll understand the reverse usage of the reverse function better if you remember this particular detail. So what the sorted function using the compare instance and this key does is it sorts these classes. Remember, the result is the fact that the root class is here, then the next subclass, and the lowest level subclass is at the right end of the list that it returns. Okay, so that's what happens when you apply the compare instance or supply the CMP instant as a key and then sort a dictionary of classes. Okay, so if we run that, and then you run this, what you see or get as a result is a sorted list of classes with the root class on the left and the lowest subclass on the right. Just like we saw the annotation return function, he also defines a P2 anno, again, a helper function, which is used to grab the type annotations, and it's used to grab the first two type annotations of a function. In all fairness, I'll tell you that one of the things that I haven't discovered the complete, or I haven't resolved myself, the complete mystery of why he captures the first two annotations of F. because in the walkthrough, he only grabs the first and then he has modified it subsequently to grab the first two. And it kind of, as you'll see in the code, the second one is mostly object. We dispatch based on the very first annotation all the time. So it's unclear whether he has done it for expansion reason or whether there is a reason even currently that he uses the second annotation for. But be that as it may, it's not material to understanding the rest of the code. But what he does is grabs the type hints, and from there, as you can see, he grabs the annotation list O for NO in hints.items if it's not returned. So we'll see in example just in the cell below that it's basically a list of annotations. If there's only one annotation, which means that there's only one input to F, which has any type annotation, then he sticks in to the annotation list. He appends object, because object is, as we just discussed, is the root class of any Python object eventually, or any Python entities. And then he returns the two annotations. The second annotation being object if there is nothing. So that we run that. And then we go through a bunch of tests where we check what's going on with the P2 annotations. So again, you check, in this case, we have defined underscore F to be A. This, now again, remember, compared to the annoret, here we are paying attention to the annotation or the type annotation of the input value of A that we are passing in to F. So we check P2 annotation of underscore F. Because there is nothing, no type annotation here, both are of type object, that's what it returns. If the, so this test checks that P2 anno should return object object in the case we pass just A with no type annotation to it. If we pass in A and B, but again, there are no type annotations to either of them or both of them, and so it continues to send us object object. Now notice what happens when we start type annotating A, no annotation on B, therefore an object, a none annotation on A, and that returns a none type. Now, here notice that the behavior is different. When there is a none annotation, it returns a none type. But when there is no annotation, like in these top two cases, it returns object. Then we look at string, the return annotation is float. So in this case, this is not something we pay attention to. We are focused on the input annotations. So this ought to return a string object, and that's what we find. And again, in these cases, you may want to comment out or focus if you're trying to go through it and learn yourself what it ought to be, and then check whether the return he's checking with is what you expect it to be. So here it's a none and a string. So this ought to be an object string or a none type and string. And so that's what you see here, a none type and a string. Now let's see a function with two inputs. As I said before, since he grabs two annotations, you will get an int and int. And that's what you see here. We'll get into this towards the end, that not only functions, but methods of classes also work with type dispatch object. And so here, underscore F is not just a function, but it's a method. And the reason it's a method is because we are passing in self as the first parameter. So it will be a method within a class. The key thing that P2 anno has to do is therefore focus on the inputs passed to the method. It should ignore the first self that's passed to it, because that just is the method instead of a function. And so again, here, the two inputs are A and B. So it's int, that's the two annotations. Here, it's an int and a string. So you expect an int and a string. And then you just say attribute getter. That means there's no nothing passed in, so it's again getting object. So that's, these tests just check and help you understand what a P2ANO function actually does. Okay, so now we begin to look at what is a type dispatch object. Now, before we get into the code to understand what a type dispatch object is and what it does, again, remember what we have done so far is try to define a meta class which will define our transform class. Therefore, we wanted to do a dunder prepare in our meta class, which returned this special type of dict called TFM dict, which was an ordinary dict, except when the string we passed to it was decode encodes are set up, in which case it created for the key of encodes decodes are set up, it created a type dispatch object. We are in the midst of figuring out what a type dispatch object actually is. And excuse me. So we kind of realized that the type dispatch object should work like a dict because we'll be adding several types to it. So again, keep in mind, as I said before, the desired functionality we want from the type dispatch object is we want it to dispatch the function corresponding to the type of the input that we provided. So typically, if we provide some input like X, we will just want some function to execute on X. In this case, we want the capability to have that function be different depending on the type of the value X that we provide to it. So what we want the type dispatch object, obviously we want to be able to add different types to it and correspondingly different function. Therefore, we expect it to be of a type of dict. Now, what I'm saying here is recall that encodes, decodes, and setups of transforms are being made into objects of type dispatch. And essentially what type dispatch, it's a way for languages to decide what piece of code to run when you actually call something. So in this instance, when we define a type dispatch object, or when Jamie does, what he is actually aiming for is to dispatch different pieces of code depending on the type. So what we want for type dispatch is something that looks like a callable. So it has a call, but when you call it with an argument, we are not just going to call the function, but we're going to look up the type and we're going to find the appropriate function that corresponds to that type within an encodes, a decodes, or a setup, right? And then it will call that function and passing the X that we are passing into it. So now when we look, we are right about at this point in the description. So let's jump into the code, but just a reference before we jump into the code is, here's kind of the example of a transform encodes that we can kind of refer back to as we go through the code. What it means is, and we'll later on learn how the transform class works as a decorator, but assuming it does for now, you can define @rotate as we've seen many times before, and then define an encodes for it. Actually, we define a rotate class, make it a transform, inherit from it, and then make rotate a decorator, and then define an encodes, and we can define whatever the function is. If it's a tensor, we can define a different function if it's a tensor image, yet another function if it's a bounding box, blah, blah, blah. So now, having the background of what we talked about, we want type dispatch to be a dict, but we want its call to have the capability to dispatch depending on the type. Let's dive into the code and see whether it does something similar to what we anticipate. So this is the class type dispatch. And as he says, it's a dictionary-like object. And this is an important comment. Get item matches keys of types using subclass, and we'll see what it means by that. Let's look at the call, because that's where we said we would want it to behave in the manner that I just described in the paragraph up above. So what it does is, when you pass in an argument, it makes it into an L, or L, if you recall, is a special type of list. So it just converts it to a list, maps the type onto the first two instances of the args that you pass into it. So basically, TS is type mapped to the first two values of args after making an args into a list. Okay, and then convert that TS into a tuple and call self, again, index. Now this self and then the square brackets actually means, and remember that this type dispatch is of kind of a dict. So this particular format essentially, or this line of code, is actually calling self.dunderGetItem of the tuple of what is passed into it. That is, it uses that guy as the key to the dunderGetItem method, because our self is a type of dict. And the dunderGetItem is the thing that helps us get the first matching type, that's a superclass of the key that we passed into it. So I don't really get why it converts TS to a list, converts it to a tuple, reconverts the key that's passed in to an L, but be that as it may, here you get a list.
I think.
Go ahead.
Yeah, I think that is to be able to use the map of L, the first conversion to the
Sorry,
list.
you can't quite hear you.
Okay, sorry, can you hear me now?
Better.
Okay, yeah. I think it is to be able to use the map of L, in the TS. L has a method map. So when you convert it, when you do the mapping to type, you convert it to a tuple so that you can pass it into get item, as one collection, as a single collection.
Yeah. No, I get that part, but then, he converts it to a list, then converts to a tuple, again back to a list.
Yeah, you can't pass into get item. It has to be either a tuple.
Yeah, it has to be a single value, so he converts it to a tuple. That part I get, but I was just wondering whether there is a simpler way to do that, because it goes to multiple conversion, but not material to what he eventually ends up doing with it, which is more important. But I get your point that you're just pointing out that you need to you need to pass in a single value k, which therefore it's important to make that into a tuple in order to be able to pass k in as a tuple. That is a single entity to a get item, right?
Yes.
Yeah.
Yes, that's it.
Yeah. And he converts that to an L. Again, remember that he uses, as I said, with P2 ANO and stuff, he wants the first two types. And if there isn't a second one, he appends an object to K. And that's why he does the if length of K is less than 2. And then, and this is the important part where we begin to also understand type dispatches details, if you will, even more. The next line in the code says self.funcs.allMatches K0. So what you observe up above in the type dispatch is you begin to see that there is something called self.funcs that you pass, and funcs is just a tuple, basis is an empty tuple that you pass in to the type dispatch object, and self.funcs is of type dict. So it's again self.funcs within type dispatch is a special type of dict, and we'll see in a minute what that is. The code for type dict is right here. Okay, and we'll see why and what's special about the type dict in a minute. But back to where we were in type dispatch. So self.funcs is a dictionary, and self.basis is again list of bases, and we'll again come into why the bases are necessary, but with some filtering done of not none, and then stick in, if it's not none, you find out all the bases of these funcs and stick them into an L. So while self.basis is a type L, self.funcs is a dict, type dict. Now, then where we were is saying self.funcs.allMatches. So what it's doing here is it's taking the dictionary self.funcs and executing all the matches for the 0th index of the tuple that we passed into K. Remember, the tuple is just the first two types, right? So K0 is the first type, and it finds all the matches for the first type of the arguments that we pass in to the type dict. That's essentially what it's doing up to this point. And if you look at all matches is the method of self.funcs. Self.funcs is a type dict. So if you look at all matches code of a type dict, then this is the code that helps us find all of the matching functions, if you will, for the type that's passed in. So K here is K0, as we saw in the code. Here, this K0, self.funcs.allMatches, and then K0, which is the type, if you recall, of the arguments, and it's the first type or the type of the first argument. So now what happens in type dict, because we are executing the all matches self K, which is K0. So here what is happening is that all the types that are coming into this particular entity, type dict, for which are registered, for which there is the appropriate subclass relationship, what it does, and it creates a list of types. So it's unfortunate, at least for me, that he uses F, but here it's just a value, it's not a function. So what this line of code does is it just creates a list of types if the type is of appropriate subclass. And it uses the dictionary self.d. So what the type dict, remember that again, I like to orient myself repeatedly because otherwise I get lost buried in the details. We have within the type dict, which is the self.functions is of type dictionary, and that in turn, the self.funcs is a type dict. The type dict has two dictionaries buried in it, and we'll shortly figure out why there are two. One of them is a cache, and the other one is a dict. And the cache keeps a sort ordered function, sort ordered value of the various types. And for example, we went through the three types: int, numbers.integral, and numbers.number in the previous example that we went through. And remember that int, which is the lowest subtype, was on the rightmost of the list. And here in self.d, if you kind of conceptually continue to think of that example, what it is doing is it's sorting them, those, let's say, these same three classes, but the reverse equal true means that int is flipped to the left of that list. That means that when you grab the first value from self.d, you will get int, because this reverse is true, would mean of those three classes, int, numbers.number, and numbers.integral, numbers.number number will now be on the rightmost, numbers.integral will be in the middle, and int will be on the left. That's what happens when you execute the self.d. It gets a sorted value of the subclasses. Now, what happens is you want, as part of the type dispatch infrastructure, to grab the function corresponding to the type that's the lowest subtype. You do that by sticking this, let's say, int class, which you will get from self.d, into a cache. But if that key, remember this key k is k0, which is the type of your first input that you pass into it. If it's not already in the cache, then you create a list of types and add it to the cache. You add it to the cache by doing self.do for o in types, which is this types. And then you return the self.cache k, which means what you've done in this code is essentially, if the key, which is the type, is not in the cache dictionary, create a list of types, add the value of whatever this right-hand side of the this particular line of code is to the as the value for the type k, and then return that value. The reason we go through this trouble is because the next time we come in, if it's already in the cache, it'll skip through and just return this. So this lookup of, oh, is it the lowest subtype, and am I returning the correct function corresponding to the lowest subtype? It takes a little bit of time to execute each time because it has to go through the check. And in order to speed that up is why Jeremy introduced this two dicts, self.d and self.cache in, and the type dict. If you look at his walkthrough, this detail is not there. The code is much simpler, but obviously he found that it was executing much slower. So he made all these changes in order to speed up the lookup of the type indexing to the function that it's grabbing by sticking the value in the cache for each lookup, so that subsequent lookups return much faster if the key is already in the cache. Okay, obviously this is a lot of detail, and as he repeats, even at the beginning and the end, you don't need to understand any of this to use it, but at least I find it useful, if only to improve my debug capabilities as I go through and modify stuff to make things match, and I'm able to chase different parts of the code, and I understand better how Jeremy thinks in his style of coding, so that I can kind of guess at what his intentions are as I go through more and more of his code. But those are more of the reasons to go through it in such a level of detail and try to grasp what he's trying to do. So yes.
What is that comment of line just underneath, let's say, def dunder get item?
Here?
Yeah.
So what it means, best I can tell, is this, right? Let me go, let's stick with this example, okay?
Mm-hmm.
If in this example, if, for example, let's say, and well, let me use these two, tensor and tensor image, to illustrate what I want to illustrate. Suppose you define an encodes for tensor, but do not define an encodes for tensor image.
Mm-hmm.
Okay. Or in fact, let me do this. Let's say bounding box, for the purposes of our discussion, is a subclass of tensor image. Okay.
Okay.
And tensor image is a subclass of tensor.
Mm-hmm.
Okay. Now, let's say I define an encodes for tensor image, and I define an encodes for tensor as I've done here. I do not define an encodes for bounding box. Okay. Now, when I execute the infrastructure and try to execute an encodes for a bounding box, remember that I have not defined an encodes for bounding box. So this does not exist.
Right.
Which of these two should I grab?
Okay, I see.
Is it tensor image or is it tensor? And the answer is it's tensor image. It's the lowest superclass of this subclass.
Okay.
And that's the reason he has to sort through. And the example I gave is that of int numbers.integral and numbers.num. Think of that troika. If you don't define for int, you define for numbers.integral and numbers.number, and you want to execute an encodes for int, which of the two, numbers.number or numbers.integral, should you grab?
So shouldn't that be the subclass rather than superclass then in that comment?
No, but it is grabbing the superclass, right? The lowest superclass. See, int is a subclass of numbers.integral is a subclass of numbers.number. In other words, numbers.number is a superclass of numbers.integral is a superclass of int.
Okay.
Right? So by saying that it grabs, oops, I overshot. That guy. Yeah. So first matching type, that's a superclass of K. So if I get int, obviously I'll stop because it's the lowest subclass. The next superclass of K, which is numbers.integral, if it's defined, that is the first matching type that's a superclass of K. You got it?
Okay. Yeah, that makes sense. Yeah.
That's why.
Yeah, cool. Yeah.
Any other questions? And it took me a while to also figure out what the hell was he doing reverse. And then I figured out, oh, compare instance sorts it in the opposite of the way we want. And that int example clarified it for me. Because if you saw when we used this up above, it first put int on the rightmost side and then integral in the middle and the numbers.number on the left. Whereas, or, you know, what we want is the reverse order if we are grabbing the lowest. So we'll try int first, then, or at least try to grab that first. But if that is not, then it's not defined, then it'll grab numbers.integral. And if that's also not defined, then it'll try to grab numbers.number. Or at least that's what it'll stick into the cache.
Yep.
Okay. So that kind of tells us a bunch of detail about where we are here. So this now explains what I just went through in our code. So inside our type dispatch is a tick called funcs, which is self.funcs, where the key is the type. So for example, when we look at rotate, the keys that we'll have, the Ks that, or the K0s and stuff that we paid attention to would be things like the tensor image, the bounding box, and the values are the appropriate values of the encodes, decodes, or setups to call for each key, which will be the type. Now there's an add methods, which is what TFM-dict calls. As you saw in the transform dict.add code in our prepare, I'm now switching to O4 transforms code just to show you the place where, am I going in the wrong direction? Let me make sure I'm looking at the transform meta code, transform dict, and then transform dict does an add. This add is what is adding the function v, which is what we are passing in. So that is the add of the function. The add method finds the type annotation using P2ANO, and if ANO is none, obviously it assumes object, which is the highest level, blah, 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 pops it into a funcs dictionary. And later when we call, it goes through the call, then extracts the tuple, goes through the get item in the self.funcs dictionary, gets the type. If there is no type, which we saw in the P2ANO, it can happen that there is no type, in which case it returns arg0, which is nothing but returning X. And if you call rotate, depending on the type of stuff that we pass into it, that is the type of X value that we pass in, is it a tensor image or a bounding box? Sorry, this statement actually says if you call rotate with an int, instead of types that we've already described, then nothing happens because the type doesn't match. If we pass, and we've seen all this in when we used the transform code, but this is just a repetition with respect to how it or what it's actually executing. Then if we do find a type match, then that function is called along with passing args and keywords out. Now, one comment I would make is we will see how type dispatch works actually with some examples and tests in a minute. It's somewhat unfortunate, but I don't know that we could have done it any other way. In this one instance, we actually worked bottom up in the sense that we explained the code before we started using it. That kind of keeps this a little too abstract, but it'll become more concrete as we get into the details in a minute. And then the other key thing which we'll talk, hopefully we'll be able to finish that today itself, would be that this works not just when the function passed into encode, decodes, and setups are just functions, that is functions existing independent of any other class. It also works, and this is a really very fascinating and interesting thing that you can dive into. It also works if f is actually a method of a class. So that's something we'll see as well. And then this rest of the paragraph is what I've just explained. How does it look up type? You go look through the get item code, and we keep a cache. That's the reason why in type dict there is self.d, which is just the list, but it's an ordered or sorted list of a sorted dict of items, I should say, not a list. It's a sorted dict, and it's a dict mapping from types to functions. And we need a special cache. Why? We keep it in a cache because every time we look for it, if it's changed, then we need to find the appropriate value. And if that value is already in the dict, then we don't go searching for it, but just return the value if it's already there in the dict. And if we don't find it in the cache, then we have to do the matching in order to return the appropriate value based on the all matches method of the type dict. So the other thing which is interesting is also now that a level of detail, well, this particular first two lines, or these last three lines just explain what I just explained, which is it walks or at least checks the lowest type class. But actually, if you look at the code, because if you pass it the basis, and we'll see that I believe in the transform, but the reason the bases are important is it needs to remember that it creates a list of bases, and in the get item, it also walks the bases if there is not a match at the lowest subtype, because it needs to check them, as I've said before, to make sure that one of those, if it's defined, it gets to use it. And we'll see that in an example. So with that definition, and we'll get to how it uses a method. So I've kind of skipped through this piece of code. Remember, we are in the type dispatch class. And as I said, type dispatch basically means if you call a function, it matches the type, it uses the dictionary type. It's a dictionary, so it uses the get item to get access to the right value. And then if there is no function corresponding to it, it just returns X. If there is a function, it calls that function with args and keyword args. I have kind of ignored this particular line. I'll explain that subsequently when we are using examples. This line is where, this line explains, the single line and some and these 3 lines of code is what makes the type dispatch work, not just for functions, but also when the functions are buried inside classes as a method. And we'll understand that in the examples in a minute. So let's go through some examples. Oops, not what I wanted to do. Okay, these I'm going to skip. You can go through it yourself. These were just things that I was playing with to understand better what P2 annotation returns when you see different types. I've kind of already explained it because I understand that better now. So I'm kind of going to skip through these, which are more my own. Let me figure out what P2 annotation is doing cells. Now let's look at what a type dispatch object does and what it is. So we define various functions. Remember, these are just functions. And we define types for their inputs. And then we define return attributes as well. And then go through these. These are the definitions. So now we have created T, which is a type dispatch object. We pass in a bunch, essentially a list of these functions to the type dispatch object. Remember that type dispatch has the self.funcs. So what we have done is loaded self.funcs to be that list, right? Now, the thing he's pointing out is you can define the same function multiple times. It doesn't matter because the way the infrastructure is set up is once, and in fact, if ni2 function is defined with different values for the type of the input, then obviously it will point to different functions. In this case, the way he has it set up is each function is only pointing to, or I should say each function has one input and of a particular type. So these are all unique functions with unique types for their input. But you can define the same function twice, it doesn't change there. Now, the way we will tap into each of these functions is because self.func is a dictionary, it will be by indexing into the dictionary. So T key will point to the appropriate function that needs to be dispatched based on the matching with its input type. That's what you expect from a type dispatch. So treat T or type dispatch like a dict, passing in the type, which tells us what function should be called. So if we pass in T int, what we should get back is the corresponding function that should be called when the type of the input we pass in is an int. So again, you can go through and check or mentally check and then execute the code to check that what you expect is what you're getting. Test equal T, you pass in the type int, what you get is fni2 because it's of type int. That's the lowest type which it matches for fni2 because the input type or the index, which is the type, is int. Now, look at this example, which also clarifies the answer to the question that Raquel had asked, which is if we now choose np.int32, again, if I pass, I kind of showed you the class hierarchy of numbers, and in that class hierarchy, int is the lowest subclass if it matches, but in this case, it's not an int, it's numpy.int32. So it will not return this function, but it's still an integer. So it'll match numbers.integral. It won't go to numbers.number because numbers.integral is a closer type match than numbers.number from within the class hierarchy of int, numbers.integral, and numbers.number. So what we would anticipate is the return function should be fnin, which is what it is. And that's the comment I have on top of that. And then if we try to match string, there is no string, so it'll return none. Match float. Now remember, float is a number, but it's not an int, not a numbers.integral. So what we would anticipate it to match is fnum because it's numbers.number, and that's what it does. And then Boolean or list. Now, if X is a Boolean or a list, then it should return fbll, which is what it does. And then let's see if it is, and then he adds the fcall, which is of collection, and a string is of type collection. Therefore, if you pass in a string, then it matches typing.collection. That's why it returns an fcall. Okay, now here's the important difference between calling a type dispatch object and indexing into it using a type. See, remember, T is a type dispatch object. So T of key, such as we've been doing all this time, is actually indexing in and into the dictionary and returning the function corresponding to it. But when we make a value, so O is a numpy int 32 value 1. So it's a numpy integer. So what would we expect the function to be called? Well, the function would be nin because numbers.integral, as we saw before, and therefore it ought to return us 2. But the way we call it is, it's not, we're not calling the, or I should say, we're not indexing into the dict. We actually want to call this function fnin and pass in the x value. So that's why here we say t dot returns O, and here it returns the int, test equals, so t O is 2. So here, if you notice, we are actually calling the function nin. So it's a callable, so you pass in these brackets as opposed to the square brackets for the function that we want to return, matching the type. So in this case, we're actually calling the function passing in O, which has a value, and therefore this function is actually executed and the return value is 2. So test equals t dot return. So int, it just says, hey, because I'm returning, and if you see here, we have typed the return of fnin to be int. Therefore, t dot returns. This is using the anoret function, helper function that we saw before. So it's comparing that type to what is going to be returned, this x plus 1. So it says, or it checks that our infrastructure has successfully typed the return value 2 to be type 2. Okay, that's what it does. And then this thing just shows that, hey, this is the way that the type dispatch object is indicated. So you can, if you want to debug and or find out what is being dispatched on what type and whether you're getting the right values, you can print the type dispatch object and see what function is being called. Okay, now here comes any questions on this? Because this is actually where you begin to grasp the functionality of type dispatch and how all the code we went through, even if you don't understand the nitty-gritty details, how it's expected to work. Any questions? Okay, moving on. And I would say probably this particular set of lectures or last and this one are the most intense in terms of Python code and the details of how he navigates through the various modifications, multiple dictionaries floating around with multiple levels of hierarchy. If basis, remember that in type dispatch, we also saw besides the funcs, we pass in basis, which is typically an empty tuple. And what happens there is the fact that if basis is set to a collection of type dispatch object, then you search through them if no match is found in the current object. So that means if you have a type and you give it, if you have a set of type dispatch objects, then you search the basis as well if no match is found at this level of the hierarchy. So this is what the for base in self.basis code in the under get item method does of type dispatch that I pointed to before here. So this guy here, these lines exist in order to search through the self.basis if the bases are provided as a collection of type dispatch objects. Okay, that's what these set of tests do. That is, so what he has done here, you can see, is he has added to, he has made it these objects that we these functions that we already defined as the basis and passed it in to the type dispatch of this particular function. So T2 only has this function f string, but in its basis has all of these functions defined as well. So when you do that, then if you dispatch on T2 for an int, you're still able to find fni2, even though T2 itself does not have a definition for fni2. And the reason for that is you have said, oh, I'm passing you bases to search for, which include all these type dispatch objects. And you can go through and run this code and understand that it does pretty much this, except that it executes this code, and on top of it, it's also able to call any of the functions defined in basis. So that's all this does. So I'm going to go through that. Oops, I guess I didn't run this guy. Oops. Right. I have never ran type dispatch to begin with. Did I run everything on top of that? I didn't run that either. So let's run through all the code in order for our examples to work. These are just examples, so those wouldn't be necessary. This is one of my little annoyances with Colab is it doesn't easily tell me whether I ran it. It just kind of gives me back the same, and that's an annoyance that I wish they would. Oops, what happened? Type dicta. This is the problem with not executing code in order. Okay, type dict. Type dispatch. Sorry about that. I do not need to run those guys. Thank you. That should work. Okay. Now, the last thing I wanted to explain here is this particular piece. Hopefully will take us 15 minutes and we'll be done, and we can go to pipeline starting next. But this is actually getting into, in fact, lecture 6 a little bit, but it's relevant mostly to lecture 5. So here, what we see is we have defined, or Demi has defined a set of functions, but unlike the other functions that we have defined before, like f string, which is just a function, so you don't see a self. If you go here, you don't see a self. These are just standalone functions. Now look at these guys. They are actually methods, so they have a self in as the first argument. And then the rest of it is similar. You just define the type of the input that you're passing into the method, and then you define what values you want return. So the point here being that, again, you create a type dispatch object. Notice the difference between how we call these standalone functions versus how we are calling the function here. The T is a list of type dispatch functions as before, but we have defined a class A, define a function to be the type dispatch, and instantiate the class, and then call a method f of the instance of the class A. And A.f is the type dispatch object. But remember that now f, which is our type dispatch, is actually a method of an instance A, right? So the question becomes, how did Python or our type dispatch object know that A.f should be passed a self as well as the value x? So if type dispatch were just a normal object, then you would not have the ability to dispatch to both functions, which is just f, and instances of a method such as A.f. The reason that the capability exists, we'll look at in a minute, but the point is that there's nothing which says A.f, which is just an attribute of a class, should be passed as self. So how does that magic happen? It happens because the short form of it, for those of you who are experts in Python, is type dispatch is also a descriptor. So because it's a descriptor, it has to have a get, a dunder get, which enables you to pass an instance and an owner. And that enables you to have the ability to distinguish, or not distinguish, but also support methods of classes versus just functions. So what happens here in the normal case, forget about it being a method. In the normal case, if we find it to be a function, we just call the function. But what if, as in the particular example we are focused on right now, f is a method of an instance A of a class capital A? Then we turn it into a method instead of a normal function. And how does it happen? So it happens this way. It checks whether this particular class, that is a type dispatch object, has an instance. So it does that by executing this line of code. If self.inst is not none. So if it is not none, that means an instance exists of the type dispatch object. Then we make the function a method of the instance. So now we have bound the function f to the instance of this type dispatch object. But the question then, we have answered part of the question. We have now figured out how type dispatch objects support methods as well as function. But how does it know that it has an instance, which is self.instance? And that's where this dunder get comes in. And as I answered before, the short answer is that type dispatch object is a descriptor. So what is a descriptor? I've again provided a bunch of videos and reference documents. It's really a fascinating piece and a very fundamental piece of Python code of what descriptor does, because descriptors are what allow you to access all the attributes. It runs in the background in all instances of attribute access for Python. So it's very fascinating. Properties work through descriptors, and you can do a lot with descriptors that you can't otherwise. So if you want to really get into the details, I'd encourage you to go through these text as well as videos. But sticking to the answer here, how does type dispatch know what self.instance is? The short answer is it's a descriptor, but the longer answer is, in Python, when you say a.f, what happens is that Python in turn calls a special method dunderGet of whatever class f is in. And again, you can go to this data model reference section, customizing attribute access. And there's a whole bunch of references, some of which are here below, writing and implementing descriptors. So dunderGet in effect gets called, and dunderGet interestingly gets two things. It gets the instance, which is the small a of what we are doing way down below here. So this small a, which is an instance of this class A, capital A. So capital A is the owner and small a is the instance. Keep that in mind, because what happens when you have a dunderGet in type dispatch is this instance inst is small a and this owner is capital A. So what you end up doing in the dunderGet is you make the instance of the type dispatch object, that is self.instance. So the instance of the type dispatch object is made equal to the instance A in which f exists. The owner is capital A, but the instance is small a. And then you return self. So now this self, which is the type dispatch object, has an instance. That's why when you check if self.instance is not none, then you will find it's not none when you have instantiated small a. Therefore, the function f will get bound to self.instance. And then what you're returning here will not just be a simple function, but will be a method. So that's the magic of how a type dispatch works, not just for standalone functions, but also for methods. I mean, obviously, I'm not explaining how it is descriptor works, but essentially the dunderGet is what enables you to have the capability, because it gets past the instance. And by making that instance the same as your type dispatch object instance, you're able to determine that there is an instance and therefore wrap a function and into that instance and make it a method. So that magic is the reason that when you execute this piece of code, you find that a.f of 1 will be, again, it's 1. So I guess it'll be numbers.integral. Again, see the magic that it is numbers.integral before numbers.number, and therefore it converts the string, converts the input x to a string. So 1 is converted to a string and then another 1 is stuck to it. And that's why you get a.f of 1 to be 1, 1. Okay. And then if you pass in a float, then numbers.number is what is called. So it will just return that. So float f1 returns 1. Then you check that test is a.f.instance is a, yes. So method check. So that says that somehow it's binding a self to this object a.f, which is what I've explained above happens. And then if you pass in false, which is a Boolean, then as a result, the attribute of self is set to a, which is what you check. And that's what happens here. So if you run this, you shouldn't expect to see any difference, and take a few more minutes to just wrap this up. You define mtup, which is an X is a tuple, and you pass in the values. You can again go through this. He just instantiates, calls F1. Again, you see the same thing. F of 1, you see the same thing, false. So this test is just executing that when X is a tuple. It behaves the same way. Remember that it will execute for each instance, each value in the tuple. Again, this is just checking that the float is executing properly. There's an interesting check because you pass it to, but you make sure that the appropriate match is happening based on what ANO returns. So you can run that and check that the expected results are what you would anticipate from this set of definitions. If there are any questions, feel free to contact me on Slack. So that pretty much covers, yes, go ahead, question.
Like the core arguments in type dispatch is a function that returns a function. I don't know, is that what's, because that's like, it's basically, is that what makes it a decorator? Can you start? Oh, okay, yeah, see the heading.
Sorry, I can't, can you
just
be a little bit louder? I'm missing your question.
Huh?
Yeah, can you repeat, please?
Oh, okay, I just saw the heading now. I was about to ask if it was because of the call in type dispatch returns a function, so it can be used as a decorator. Then I just saw the heading under type dispatch decorator.
Yeah, we'll, in fact, in the next lecture, we are almost out of time. So in the next lecture, what I'll do is just we'll return back to the transform notebook. We have covered kind of the complete type dispatch object. We'll return to the transform notebook, clean up. Remember, all we have focused so far, just to summarize, is we have gone through the prepare portion of the TFM meta class, which helps us return a transform dict. We saw transform dict introduce type dispatch objects. So we went into the type dispatch notebook to understand what type dispatch objects are and what they do. Essentially figured out that they are nothing but dicts which help to dispatch functions or methods depending on the type. We saw how all that worked. And then we'll get back to the TFM meta class in the next lecture to wrap up what the other two methods that we are modifying in the meta class, the dunder new and the dunder call do. And the dunder call of the TFM meta class is what helps us make the transform class a decorator, and we'll get into that in the next lecture. And after that is finished, because that shouldn't take a very long, maybe 15-20 minutes, and then we'll move right into lecture 6, which is using pipeline. But this is in a lot of ways the most intense code heavy part of the library, but going through it in this detail really helps understand the functionality, and at least to me helps me become a better debugger and understand the way Jeremy codes his library.
Yeah.
Any questions?
Send the notebook on the Slack.
Yes, I'll post this, and as Joseph said, one of these days, hopefully this coming week, I'll be able to dump all of my notebooks into GitHub, whatever state they're in. Keep in mind that I keep modifying stuff on them. So for example, the transform notebook, I've changed in order to explain pipelines and a few other things as well. Yes, I'll post the 2 notebooks right after this class on Slack, but eventually, as Joseph suggested, which is a good suggestion, I'll just dump them on GitHub.
Yeah, sure, thanks.
Any additional questions before we end? So next time we'll kind of, it's end of walkthrough 5, but I've already covered a bit of walkthrough 6. So it's walkthrough 5, 6 that I'll be getting into much more of pipelines and then wrapping up just the definition of transforms. Okay, not thanks everybody joining.
Okay, thanks.
Thanks, Srinivas.
Thank you.
Bye.
Hello.
Yeah.
Not a question, but a suggestion. Right now, there are one guy trying to write like documentation for fast core, and I think these notes could also help on that. Maybe you can try to make a peer request for documentation on this. I think they will accept it because I think it is extensive, and well, I think that could help also people understand that. If we link.
Yeah. What you're saying is that you should like contribute to the document. Hamel is currently writing some documentations for FastCore.
Yeah.
So some this type dispatch is from FastCore. So I think it will like really be helpful because the documentation now should be shallow.
Yes.
Yeah. So Srinivas, you may want to get in touch with that guy Hamel Hussein, who's helping out with the documentation, because it's a great idea. I think you've done a lot of work that could be really helpful to publish on the in the documentation.
And also there is some people asking about if Jeremy will do like a second walkthrough, but he says that not. Maybe we could try to invite people to this. Maybe they didn't get the first part, but they will see the rest.
Yeah, okay. The thing is this part, the fast AI, I think what people want extra work on is fast core, more sure. Yeah, that's what I heard, I saw rather, fast core, but this is mostly just fast AI, like not the core part, not the fast core part. I don't know if that makes sense.
Oh.
But it will still be helpful anyway.
Yeah, these are 2 cores part, but they're also, the earlier things we went through were the fast AI notebooks, like the block, data block, and a few other things. And again, we'll be going through that in the tabular part is completely fast AI, not fast core. These are the core. These 2 notebooks and the next one are core. So, yeah. Okay, we'll dump those in a GitHub and try and get in touch. If somebody can post the name of the person, I didn't catch it, but if you can post it in Slack or send it to me, and I'll reach out to the guy and point him once I put.
I'll post his name.
Great, thanks. Okay, thanks everybody. And if you have questions or even clarifications to what I haven't explained well, feel free to send me a note.